is introduce it briefly. And then on Monday, when we get here on Monday, I'm going to spend the first 15 or 20 minutes. We're going to be looking at geometric isomers. I'll have a few examples for you. And then we're going to do an activity with these kinds of models. Similar to what you did in the Chem 1 class that you had. I think everybody here has used these before. Yes? Yes?
Yes.
No. Okay, now before we get to geometric isomers, I want to show you something else, something that you can stand on. If I have this compound, and then I have this compound. Are these two compounds the same compound, or are they isomers, or are they different compounds? Isomers. I heard some isomers and some same. What is the name of this compound? Name everything the same way. Find the parent chain. What's the name of it? 2 carbons. Ethane. Ethane. Yeah. And it does have a functional group on it. Chloroethane. We want to call it 1 chloroethane or just chloroethane? Does that work? Just chloro? No 1? Okay. All right, so we're going to call that chloroethane. As I write that, what's the name of the second compound? Still just chloroethane? You don't want to put a number on that one either? Are we convinced that these are both the same compound? I have a model of it. Here it is. The blacks are carbons, and then the hydrogens are yellow, and then the chlorine is blue. This carbon has 3 hydrogens on it, and the chlorine is like that, down, underneath the first carbon. What do I have to do to this model to get it to look like that? Do that again with your hand. Thank you. How about this? Now is that a model of the second compound? Yeah. Did I change this thing? No, if I do this, I'm not changing anything about it. Single bonds between carbons, they always have the freedom of rotation. They can rotate. And so when you have a functional group in one place on a single bonded carbon, and then you put it someplace else in a single bonded carbon, you're not changing anything about it because a molecule can twist and it's not a big deal. So these are the same. I'm going to erase that. Now I'm going to give you another 2 compounds. I want you to ponder what the name of this thing is, and I'm going to draw another compound over here. Okay, what's the name of this? Do the same thing when you're trying to name every time. Find the parent chain first. How many carbons in a row do you see? There's 4. There's not 2, there's 4. 1, 2, 3, 4. It's okay, there's a double bond in there. And then I drew it like that. There's still a continuous chain of 4 carbons. You with me? What's the name of it then? What's the prefix for 4? Bute. Yes. No hydros. We don't have hydros. What was the ending though that you said? Ene. Would you agree that it's a butene? Because it's got a double bond in it. Is there anything, would we just call that butene? We've got to be more specific. 2-butene. Right? 2-butene. Because we have to indicate where that double bond is. So this thing's going to be called 2-butene. How am I doing? Pretty good. What's the name of this one? Another 2-butene, isn't it? There's 4 carbons. 1, 2, 3, 4. there is a double bond between two of the carbons, so this one would also be 2-butene. Okay, now, like we saw in the first set of two compounds, this, in order to go from one to the next, I just did a little twist. Well, I have a model of this one now. I didn't put all the hydrogens around my CH3s. I hope that's okay with you. They're there. There they are. Double bond in between those two, indicated by two springs holding those two carbons together. Carbon, carbon. What would I have to do to this to make it into that? Just do a twist again, right? I can't twist it. This double bond is preventing me from twisting those this side of the molecule like I was able to when I only have a single bond. Oh, no big deal. You can twist it all day. When you have a double bond, I know this is just a model, but in reality, if you remember, a sigma bond is the electrons are shared directly in between these two. The pi bond is sharing above and below. The presence of that pi bond does not allow that bond to rotate. Oops. Broke my pi bond. It doesn't allow that to rotate. So it turns out that I cannot take this and just manipulate it and make this. This is a different compound than this. So if it's a different compound, we are going to have to name it differently. Even though both of them, we will look at it and say, oh yeah, they're both 2-butene. And there's not much arguing about that. This compound looks like this. This compound looks like that. Well, I'm just hiding a hydrogen with my hand there. You see there's a difference between those two? And they're not interchangeable. I cannot take this and manipulate it and make this without pulling bonds and moving bonded things. So these are considered isomers of each other, even though they have the same name. So these have the same name. They're not structural isomers then. They're called geometric isomers. All right, so how do we name these two things to differentiate their structures? Here's how we do it. I'm going to show you this, and then we're done. Well, obviously we're done anyways, 1 o'clock. If you have the parent chain starting on one side of the double bonded carbon and then continuing on the same side of the other double bonded carbon, we're going to indicate that that phenomena that they start and end on the same side of the double bonded carbons. The prefix that we're going to use is cis. The name of this thing would be cis 2-butene. The prefix cis means that the parent continues on the same side that it started on. If the parent starts on one side of the double bond, but then it continues on the opposite side, the parent chain is kind of continuing across the double bond. The prefix for across is trans. So that's what we're going to be dealing with starting on Monday. This is tough, yeah.
What if we're more than 4 carbons? I mean, it's going longer.
It's fine. How about we do this? That's a 3. 1, 2, 3, 4, 5, 6, 7. That would be a heptene, right? That would be 2 heptene. Is the parent, is the molecule. But still, that parent continues on the opposite side, so we would call that trans 2-heptene.
See if it goes back up.
Well, how's it going to go back up?
Like if you make a CH2 a CH.
Oh, another double bond? We're not going to see any molecules that have 2 double bonds in them. Or you won't have to name them at least.
What if we make the CH2 a CH, connect another H?
With this one?
No, the third one.
That one?
The third CH2.
That one?
Yeah.
What about it?
If we make it a CH, and then connect another H.
Where? Huh?
If we're taking one H off.
All right, hold off on that. It's a time, we are out of here at 1:03, so yeah, just hang on to that question for a moment.